I would like to welcome very warmly everybody who is watching this video. My name is Károly Kovács, and in this presentation today I would like to show you a calculation example with our DEHNsupport toolbox. Namely, we will use now the Risk Tool, and we will do a calculation example for a warehouse. Our DEHNsupport toolbox for doing risk analysis is existing already since 2006, when the first international lightning protection standard was introduced. And as you can see here, this software tool has 5 different modules. We will use today the Risk Tool. We have also a distance tool, an air termination tool, earthing tool, and then select SPD tool. I will not go in detail to the other program modules. We will use now this Risk Tool. Just to summarize what we will do a risk assessment and for lightning protection, and we can define 4 different kinds of risk. Risk 1, R1, is a risk of loss of human life, including the long-lasting injuries, and you can see here that the tolerable value is 10 to minus 5. Next, we can define risk of loss of service to the public, R2. The tolerable value is 10 to minus 3. We can define R3 as a risk of loss of cultural heritage, where the tolerable value is 10 to minus 4. And at last, we can define R4, risk of loss of economic value. So we have these 4 different kinds of risk, and we have to make the calculation for this 4 different kinds of risk depending on the usage of the structure we are examining. The next thing is what we have to keep in mind, that if we want to make a risk analysis, we are speaking about so-called sources. Then we will speak about damages, and we will speak about losses. These 3 thirds will make the whole risk analysis, and this will make the risk. And next, during the calculation, we will define different kinds of so-called risk components. You can see on this picture these different kinds of risk components, starting with RA, RB, and RC. These 3 belongs to the source number 1, means that we are speaking here a direct lightning strike to the building or a structure. You can see here in this icon. This is the source number 1. At source number 2, we are speaking about RN. The source number 2 means that the lightning strikes near the structure. And source 3, the lightning strikes in the incoming line, and we speak here about RU, RV, and RW as a risk component. And at last, we have source number 4, when the lightning strikes near the incoming line. In this case, we can speak about risk component of RZ. So these are our risk components. And how can we calculate these risk components? We have a very simple formula. We have to define 3 factors. One factor is the number of dangerous events, NX. Then we have to define the probability of damage to the structure. This is PX. And at last, we will define the loss factor, which is LX. So we have this simple formula, and we have to multiply at the end 3 numbers, and this will make up the risk components. X can be A, B, C, and so on. So this will be very roughly to summarize the risk analysis. We will do this calculation, and the calculation example is a warehouse, something like this. It looks like it's a usual so-called logistics center. You can see quite many of these around the M0 highway around Budapest. And we have two incoming lines. You can see here on the left-hand side. The red line means a power line where the energy comes into the building. And this can be 0.4 kilowatt or 20 kilowatts, 10 kilowatts, and so on. The yellow line is also an incoming line for the telecommunications, for example. So this will be, for example, calculation. And okay, I will just change the screen. Yes, and okay. Here is my laptop monitor, and we can start now with the sample calculation. Let's start the DEHNsupport program. Okay. So here is our software, DEHNsupport toolbox, and I changed the language to English, and I want to show you that this software is speaking quite a lot of languages: German, Italian, Czech, Slovak, French, Croatian, Polish, and so on. And here we have the Hungarian language, but today we keep the English language. And we can start immediately with the risk analysis. As you can see here, we have 5 different kinds of models: risk tool, distance tool, air termination tool, earthing tool, and then select SPD tool. And now we will use this risk tool for the risk analysis. Let's start. I will do a direct program start, direct program access. Okay. And we will start. After a while, we will start the calculation. First of all, we have to define the name of the project. This will be a warehouse. Okay. The country is Hungary. We can select the postal code, and we will go directly into the light density map database. And if we want to look for a city or a postal code, let's look for a city, for example, Siófok. Then in this region we have 3 different kind of postal codes. Let's select 8600, and here you will have the lightning density of 1.75. I select this one and I say apply. Okay. What is very important, you have to select the standard. Our software is international, really. This means that we can select not only different languages, but this program knows all the European lightning protection standards. You see here, DE means Germany, IT is Italy, we have here Hungary, and I think we will stay here with the Hungarian standard. This is NSEEN 62305. And something more, we can have a different version of the standard. As you can see, in Hungary we had already 3 different kinds of standards. That in 2006 we had the first edition of the international standard. In 2012 we had the second edition, and in some years ago we introduced a new version where we also took into the calculation the fire protection directive in Hungary, and you can also take this into account. Let's select this one and say apply. And in the next window, you have to select which risk you want to calculate. As this will be a first example calculation, to be not too complicated, I will take out the mark here with R2, R3 and R4. So we will not calculate the risk of loss of service to the public because, for example, in this warehouse project, in the warehouse we have no service to the public, we have no cultural heritage, and if we want we can calculate the loss of economical value, but in our case I will do not do this. To be able to have a short video, let's say apply, and then okay, I just forgot to make it large. So now we have the starting screen for the risk analysis. On the left hand side you see different big icons, and from above to down we can select each icons, and we have to work on the window, and when we go to losses, then we will define all parameters which is needed for the risk analysis, and at the end, if the risk is too high, we can define the protection measures here. Let's go back to the building. Here down you can see the calculated risk. Risk 1 is the risk of loss of human life. Now you can see the risk is at the moment is 0%. You can see it here as a numeric value, and the blue column which is situating horizontally, you can see the tolerable value. The tolerable value is 1 to -5, and it is great, so it is not shown the R2 and R3, so the risk of loss of service to the public and risk of loss of cultural heritage. On the right hand side of the screen, you see the project data, what we have defined, the postal code, the city, the name of the project, and the calculation basis. In this, you see the picture where you can see all the risk components, RA, RB, RC, and so on. And you can see here that we are now calculating the R1, risk of loss of human life. And at last, you can see the results. I show you, for example, not only the results, but only all the parameters which we defined during the calculation can be checked with the numerical value. And with the mouse, you can have a content-sensitive help, and each parameter is explained a little bit. Okay, let's go back to the evaluation, and let's start with the risk analysis. Here above, we can edit the object first. So this means that we have to rename the object to, for example, warehouse. Okay, and in the beginning, we will do risk analysis without protection measures, and this will be the actual state. Let's say apply, and we can start the calculation. Previously, we have selected the ground flash density, NG, and this is 1.75 lightning strikes per square kilometer per year, and this means that the thunderstorm days per year, TD, is 17.5 days. Okay, so the first, what we have to do is we have to define the geometry of the structure. We can select between 3 editing windows. Let's see the simple structure. In the simple structure mode, It's very easy. You can see it in the picture. You have to define the length of the building. For example, take it to 80 meters. The width of the building should be 40 meters. And the height of the building, we take the value of 20. And if we go to view, you can see immediately the so-called collection area is seen here. The blue continuous line is the outline of the building or the structure with these dimensions, 80 by 40 by 20. And this dashed line around the building or the structure is the collection area for direct lightning strikes to the structure. So inside this area is a direct lightning strikes. The areas you can see here, 28,909 square meters. This is the collection area for direct lightning strikes to the building. And AM is the collection area for lightning strikes near the building, near the structure. It is not shown on this picture. You can print it if you want, and if we say apply, then the geometry of the building is defined. Let's see the next one with building with height point. You can see here that we use this module when on top of the building we have a high structure. This can be a chimney or an antenna. Let's select this one. We took over the parameters from the left window. So the length is 80 meters, width is 40 meters, height is 20 meters, and the highest point of the building can be defined. Be careful, the highest point should be defined. The reference point here is the Earth level. So the highest point should be, for example, if we have here an antenna and the antenna is 5 meters higher than the roof of the building, then we have to enter here 25 meters. I show you the result in the view. The collection area of the antenna can be seen here with this dashed green line. And as you have seen on the previous window, the blue dashed line is the collection area of lightning strikes to the structure. And the dashed green line is lightning strikes to the antenna. This is the collection area. And as you see here, if the antenna is in the middle of the building, then the collection area of the antenna is smaller than the building itself. So this means that if we take this antenna and we simulate it in this model, then it will not increase our collection area. Let's say apply, and then I will show you how to define a complex structure. Here we will have a new window, and here above we have a graphical area, and down here we have a table. In the table we have to define a new line with this icon. We can add the name here. For example, this is a warehouse. Yes. The length is 80 meters, width is 40 meters, height is 20 meters as before. Okay, let's define an antenna. An antenna, we can define the name antenna. The antenna is not very big. Length of the antenna is 1 meter, width is also 1 meter, and we can define the height, for example, 25 meters as before. And here you have the possibility to enter the XY coordinates. For example, you can leave if you leave it here, with then the antenna is the left corner of the building. And in this case, you can see that the collection area of the antenna is a part of the collection area is outside of the collection area of the building itself. So if the antenna is here, the collection area of the whole structure will be larger than in the case when the antenna is here in the middle. Let's define a third part of the building. For example, we will build an office area to the warehouse, and the office area will be shown with red line. The length of the office area will be 20 meters, width is 40 meters, height is, for example, also 25 meters, and the x coordinate should be 80 meters. And then it means, you can see here that with the red line shows that the office area is on the right hand side of the warehouse. This is a typical arrangement for a warehouse. So we have defined the geometry of the building. As you can see here, we have defined three building parts: a warehouse, an antenna, and an office area. And the program, the DEHNsupport program, calculates the union of all these collection areas, and this will be the collection area for lightning strikes, direct lightning strikes to the structure. And if we are ready with this, we can go on, we say apply, and we have defined the collection area. This is the advantage of using this program, that it is very easy to define the collection area. If you want to calculate this collection area manually, a minimum is you have to use an AutoCAD or another CAD program, and it's not so simple to make the calculation for this sum of all collection areas. Okay, let's go on with the apply. So we have defined the collection area for S1 and S2. The source is direct lightning strikes and lightning strikes near the structure. The next one, we have to define the so-called location factor of the structure. The location factor can be four different kind. It means the default parameter says that it is an isolated object. It means that there is no further objects in the vicinity, or the object is surrounded by objects of the same height or similar or smaller. The object is surrounded by higher objects, or it is an isolated object on a hilltop or on a knoll. Let's say it is an isolated object. In my presentation, I showed you that if our structure is not surrounded on three sides with similar objects, you have to say it is an isolated object with no further objects in the vicinity. Let's say this as a parameter, so this building stays alone, or it can be the case that from one side or from two sides it is surrounded by other structures or buildings with similar heights, but it is not enough. Okay, so this was the so-called CD factor, the location factor. We can go on to the zones. We will have to define the different kind of zones. We have here a simple picture here which shows us the lightning protection zone concept in the lightning protection, and I suggest that we will define several zones. The minimum is two zones, two lightning protection zones, lightning protection 0B. This will be the outside of the building. I will define with this icon, I will create a new zone, and the name of the zone will be outside of the building. 3 meters around the building, and the lightning protection zone 1 is inside the building. I will create here also a zone, and this will says us to help. I will give here text inside the building. Okay, so we define two zones. LPZ 0B is outside the building, around the building, and LPZ 1 is inside the building. Here, this was the classification window, and then we can go on to properties. In the properties window, you have to define for the loss of human life, you have to define, for example, for the inside zone, for LPZ1, you have to define how many persons are present in the zone. The default parameter is 8,760 hours per year. If you make a small calculation, there are so many hours in 1 year. And if we leave this parameter with this value, then it means that the persons are present all year long. The persons are inside a building. The number of persons in the zone, this is a big warehouse, so in one, it is possible that the people are working here in 3 different shifts, and we will give here the number of people in one shift, and it should be 250 persons. And this means that we have defined how many persons are inside the zone and how long they are inside. We told that the people, these 250 people, are from Monday to Sunday, each week of the year they are present in the building. This is the so-called worst case situation, and in the risk analysis we have to take always the worst case situation. So we define the number of persons inside the zone and the time during which the persons are inside the zone, and let's go outside of the building. This can be people who are smoking outside the building at the smoking area. Let's take about 10% of these people, 2050. This means that 10% is 25. And let's lower this value so there are not always people there. For example, half time. This means that, for example, 4,200 hours per year, there are people who are smoking outside the building. So we defined the properties of each zone. We have two zones, LPZ0B and LPZ1. We have defined the number of persons and the time during which the persons are there. We can go on to the supply lines. As you have seen in the beginning, we have two supply lines. I will edit the name for at the beginning, edit conductors, and this will be the first conductor we will work on is the 0.4 kilovolt supply line. Okay, this will be only the name of it. Then we have here 3 icons. First of all, we have to define the parameters of the conductor. The line time is power supply line. The next parameter, we have to know how long is the conductor length. As if I pull over the mouse, you will get a small help. Then it says length of the line section between the structure and the first node. The first node, in this case, the 0.4 kilovolt transformer. So the middle voltage, low voltage transformer, we should know where is this transformer. Let's say we know it, and it is 5 meters distance from the building. So we know how long is the power supply line. This means the 0.4 kilovolt supply line until we reach the transformer is for 500 meters. Installation factor area means above ground. Buried means in the ground. And the third parameter can be buried cable running entirely within a meshed earth termination system. This means that the cable, the earth cable, is covered by a meshed earth termination system. It is not quite often when we can select this parameter. Let's say a buried cable for the power line. Environment factor. We can have an urban environment with tall buildings which are higher than 20 meters. We can have an urban area. We can have a suburban area or a rural area. Let's say if it is this warehouse is around M0, then let's select its suburban area. And then we have to define where is the transformer. So if the first parameter means that we have a middle or high voltage supply line and the transformer is inside the structure. And the second parameter means that the power supply line is an 0.4 kilovolt cable, which is in our case the situation, or a telecommunication or a data line. Let's select this one because in our case it says an 0.4 kilovolt supply line. And next is the conductor shielding. We should know some parameters of the supply line, and this parameter is whether this supply line is shielded or not. When it is an earth cable, it's usually shielded, but it's not only enough to say it is a shielded cable. You have to know the resistance of the shielding. We can select three different options. The shielding is 5 ohms per kilometer and between 5 to 20 ohms per kilometer, or between 1 to 5 ohms per kilometer, or the shield resistance is less than 1 ohm per kilometer. This parameter is very difficult to get because if you go to cable manufacturer, it will be not easy to get this kind of parameter, because for the shielding it is usually not given. You have to make the calculations based on the material parameters, the cross section and the length. You have to calculate the resistance. If we do not know what is the resistance, it's better to say it is an unshielded cable. And the last parameter on this page is connection of the conductor. No special condition is usually we select this parameter when we do not know anything about the supply line. Multiply earthed neutral conductor means that the neutral, the end conductor, in our case this is the so-called PEN conductor, it is earthed every, for example, 300 meter. If it is an area cable, then it is earthed every 300 meters as far as I know. If the shielding is earthed on both ends, you can select this parameter. If you have lightning protection cable or duct. Duct means that it is a cable duct made of metal and it is completely surrounding the cable. Then it is like a shielding and it completely surrounds the cable. In this case, you can select this parameter. Or if there is no electric connection at all to the building, for example, it is an agricultural structure to store wheat, for example, then it can be a standalone system. Or connection via isolating interface. It means that there is an isolating interface. It is not usual in power supply lines, but in the telecommunication line you can have such kind of supply. Let's select no special conditions, and then we are ready with the conductor parameters. Then we have to select system connected. System connected is the other end of the supply line, e.g. this can be, for example, the transformer itself. If it is a very simple transformer on the ground, then you have to know the geometrical data of the transformer. For example, the length should be 3 meters, 2 meters, the height is also 2 meters. And I say apply. This will be the geometry of the transformer. You have to define also the relative position of the connected system. This means that the surroundings of the transformer, we can say that this transformer, as it is only 2 meters high, it is surrounded by objects of the same height or smaller. And then we go on to the properties of the internal system. And then in here, you see here two lightning protection zones which we defined. Inside the building, the only parameter you have to define here is the so-called rated impulse withstand voltage of system to be protected. What does it mean? Impulse, you know, withstand voltage in Hungarian ez a impulse withstand voltage, ez a lökőfeszültség állósága a rendszernek, amit meg akarunk védeni. So this is the rated impulse withstand voltage of the system to be protected. In an 0.4 kilowatt supply line, this should be between 1 and 1.5 kilowatt. So this is our parameter. And in the outside, in the LPZ0B, we select the same parameter. And we defined already all of the parameters which are needed for the supply line. And here I will go inside the edit conductors, and I will make a copy from this conductor, and this copy I will rename it, and the name will be telecom line. So this will be the telecom line, for example. This will be the internet connection, which we will define. So these are the two incoming lines, and let's select the telecom lines. And in this case, the conductor is not a power supply line, but a telecommunication line. In this case, the conductor length should be always 1000 meters. This is the length what we have to define. It's again a buried cable as an installation factor. The same environment we have, the suburban. We have no transformer inside the building. Of course, it is a telecommunication line, and we do not know anything about whether it is shielded, and if it is shielded, what should be the resistance of the shield. And we select no special conditions. In this case, the system connected should be deleted. So we have no transformer. At the end of the 1000 meter, I delete all parameters here. And then in the properties of the internal system, I select the smallest possible value for the rated impulse withstand voltage of the system to be protected outside of the building and inside of the building also. The rated impulse withstand voltage is equal or less than 1 kilovolt. So so far we defined two incoming lines, one power supply lines and one telecom lines, and we can go on. Let's stop a little bit. The risk we have calculated is still 0 because we haven't defined losses yet. And please remember that we have to multiply three numbers together. And if the loss is 0, then the result of the multiplication is always 0. Let's select the properties of the building. What shall we do? Here, the factors of the building. For example, the first parameter is outside of the building. You have to define the contact resistance of the soil. The first parameter, we can let it as it is. Agricultural used area or concrete, wet concrete it means. Inside the building, let's select marble ceramics. It is an industrial floor inside the warehouse, and the similar value is marble or ceramics. Let's go on. Electric shock, it's a protection measures. We will select the protection measures inside the module measures, so let it as it is. What we have to define, the so-called fire factor. Officially, it's a reduction factor of risk of fire or explosion. We usually, for example, let's take normal risk of fire, and we have to think about what material is built into the roof. And if the roof is made of combustible material, combustible means that it can burn, then you can select this as a parameter, that this means that the roof is made of combustible material. So it can, if the lightning strikes into the roof, the whole building can burn down. Outside the building, it has no meaning what parameter we select here. I will select here no risk of fire or explosion. Okay, let's see shielding. A little explanation. In our we have this fire protection law, which was given by the Ministry of Interior, Interior Ministry. Then it is this fire protection law, and in this fire protection law says that we can have the different type of buildings. For example, education building, hospitals, where high number of people are present, or hotels, dormitory buildings, buildings with explosive areas. If we have such kind of buildings, then the fire protection law in Hungary says that there is a minimum. For example, if it is an educational building, the minimum class of LPS is LPS 3, and the minimum class of coordinated SPD system is SPM 3/4. As this is a warehouse, it is not an educational building. I will reset these parameters and I say apply. And you can define also shielding parameters, external spatial shielding for all zones, or for different zones you can also define shielding. In our case, let's select no shielding. And then we are nearly ready with our first risk calculation together. We go to the losses and we define the losses L1 for human life inside and outside the building. So let's see here, it's still 0. The calculated risk R1 is 0. And here, if you see here, these column diagrams, we have more than one diagram. We have 3 because we have defined two zones. One is outside the building, one inside the zone, and this is the total, the sum of the 2. And let's see after each parameter what's happening with our risk. Now let's start. Factor for touch and step voltage. The international standard says that if there are people inside and outside a building, please select typical value. I selected typical value for inside the building, and you can see that this means that the risk is 8%. Let's select typical value also outside the building. If I select this one, then we have a risk of 11%, which cannot be seen here because it's relatively low. The A value is inside and outside the building. We have a low value. This blue line means the tolerable value in total, in outside and inside the building. If we reach this value, then the risk is higher than the tolerable value. Let's go to the next parameter, factor for fire. We have a long list with the different types of usage. Let's select here an industrial application. Here it is, I have found it. We have an industrial application, a warehouse is an industrial application, and immediately what we can see here, that as I selected that inside the building we have an industrial application, the RB risk components is already very high. Here down you can see that now the risk of loss of human life is 1335%. So we are much above the tolerable value, what you can see also here. And we are still not ready with our risk calculation. Outside the building also we select industrial application. Where is it? It is here. And then we go to special hazard, kind of special hazard. We have to take into account how many people are there. And the first parameter says that the number of persons not greater than 100 and the structure is limited to 2 floors. In our case, we have only 1 floor in the warehouse, but the number of people we defined is 250, so we have to select this third parameter, which means that the participants are between 100 and 1000. Let's select this parameter, and the risk we multiplied with a value of 5, so the risk is much higher, 6631%. And on the right hand side also you can see that the value is very high. And outside the building we say no special hazard, and then actually we are ready. The damage factor for over voltage we do not have to take into account. We have to take it into account when we have a risk of explosion. We do not have in a warehouse usually, and if we are in a hospital we have an intensive care unit or an operational block of the hospital or other parts of the hospital. So we have nothing of this, so I select no loss, inside and outside, and we have no additional losses. And actually we are ready with our first risk calculation. You see what is the result. The result is that the calculated risk for the loss of human life is much greater than the tolerable value. The tolerable value can be seen here, 10 to minus 5, and the calculated risk is 6.63 with 10 to minus 4. So 1 magnitude higher than the tolerable value, so we have to install some protection measures. So let's go to the last window. I will open the protection measure window. We have a warning window that the program will create a protected database for the protected building, and then we will go into a new window, and in this window you can select the protection measures. If we select the protection measures, we will be ready with the first calculation. So what we see? We see here that we have here which risk component is too high. We have the risk components all here is shown, but only one component is high. This is RB. So here on this icon row, let's select RB. And if we select RB, in this main window, you will have all the protection measures with which you can decrease the value of RB. So the main aim for us that we have to decrease the value of RB. And what we can do, you can see here, we can install external lightning protection. Let's install. Let's start with LPS 4. Class of LPS is number 4. Let's see the result. I selected class of LPS 4. You can see here that the value is much lower. Now it's above 1000, but before it was above 6000. So class of LPS 4 is not enough. Let's select LPS 3, and we are on the right way to decrease the risk. You can see here, but it is still not enough. The actual calculated risk is 651%. What can we do? For example, we can install a fire protection measure. For example, we can select this one. What does it mean? Fire extinguisher. Fire extinguisher means tűzoltó készüléket jelent. Manual fire alarm system, ez a kézi tűzjelző készülék. Hydrants. Hydrants means tűzcsap, tehát van egy tűzivízhálózat az épületben. Fireproof compartments, az azt jelenti, hogy tűzszakaszokra van bontva az épület, és a tűzszakaszokon nem tud keresztül hatolni a tűz. And the last one is protected escape routes. Ez pedig azt jelenti magyarul, hogy vannak védett menekülési útvonalak, például ilyen lehet füstmentes lépcsőház, vagy kijáratmutató lámpák vannak elhelyezve. Let's select this one. Oh, we are nearly have reached our goal, but it is still too high. What can we do? Together, LPS class 3 and manual fire alarm system is still not enough. We can select LPS 2. It's still not enough. In this case, we have to go on with the fire precaution measures. We have to select automatic fire extinguishing system or fire alarm system. Fire extinguishing system, ez az automatikus tűzoltó berendezés, ezt bevásárlóközpontokban lehet látni a mennyezeten, ezek a sprinkler fejek, amik tűz esetén vizet kezdenek el spriccelni a mennyezetről. Ez az automatic fire extinguishing system, és a fire alarm, ez az automatic fire alarm system, ez az automata tűzjelző. If we select this one, we are already in the green area. This means that the calculated risk is 65%. So we are lower than the tolerable value. So these protection measures are enough to have lower risk for the loss of human life than the tolerable value of 10 to minus 5. So we have to select two different kinds of protection measures. And we always have to think about which is more economic. Select, for example, class of LPS 1, and in this case, maybe it is enough only a manual fire alarm system, or let's go back to LPS 2, and then you have to install an automatic fire alarm system, and in this case, the risk is lower than the tolerable value. So we have reached our goal. This was the goal of the whole risk analysis, that in the first, I show here, we made the first risk analysis without any protection measures. This was the actual state. And if the risk was too high without protection measures, then we had to install protection measures, and at the end, with the installed protection measures, yes, here the calculated risk is lower than the tolerable value, so we are on the safe side. So we are ready with the risk calculation. The last thing we have to do, we have to make a document. We go back to here. There's an icon here as a print icon. This is a printer icon, and then in the window we can select whether it is a short or a long report. You can select the language, for example, Hungarian or Italian or German. Let's stay with English language, and then we will have a preview, and then the program will create the report for the whole risk analysis. We have a title page. Yes, about the project, what is the title, and then we go on, and the end is important for us. Here is the flash density map, what we used. This was the collection area. Okay. The lines which are connected to the buildings, the zones parameter, and here the calculation result with capital number 7. This is the calculation without measures, without protection measures. You can see here that the calculated risk is too high. And with the defined protection measures, the risk is 64%, lower than the tolerable value. And you can see here which risk component was high. And in section 7.2, the protection measures are listed. The first protection measure was a class of LPS2, and then lighting equipotential bonding belongs to the lightning protection system, and inside the zone, inside the building, in the LPZ1 zone, we have an automatic fire alarm system, and for the 0.4 kilowatt supply line and also the telecom line, we define the coordinated SPD protection system. In my next presentation, I will speak about the protection measures. I will explain in detail what does it mean, a coordinated SPD protection, and why it is connected with this automatic fire alarm system. And I think this was enough, and we made together our first risk analysis in English language. And with this sentence, I would like to thank you your attention, and I would like to say goodbye. Thank you very much.